Well, so we continue with our discussions regarding the Machiavelli construction of the number of stages, and then we will be going over to the optimum design. So, therefore, what we were discussing? We were discussing the limits of the separation of or rather the limits between which the reflux ratio has to operate, and I had already mentioned that there are two extreme cases. One is the total reflux condition, and the other is a minimum reflux condition. So, therefore, under the minimum reflux condition, so therefore, for the total reflux condition, what do we have? For the total reflux condition, we do not draw out any particular distillate, right. So, therefore, D is equal to 0. Now, if you remember in the enrichment section operating line under this condition, then what do you have? V y n plus 1 equals to L x n plus d x t. So, therefore, when this becomes equal to 0, naturally the entire vapor which had gone, that same vapor is drawn, it is the same amount of liquid, it is introduced as reflux into the column. So, therefore, V equals to L, and quite naturally as a result y n plus 1 is equal to x n. So, therefore, we find that for such a case, for the total reflux condition, we find that the upper operating line that coincides with the diagonal line, and it extends from the point x d x d to the point x f x f. What happens to the stripping section operating line? For the stripping section operating line, again we have the equation, if you remember, this is equals to x L bar x m minus b x b. So, therefore, naturally when we are not withdrawing any particular product from the top or any particular distillate from the top, naturally we are also not withdrawing any particular bottom product. So, therefore, this becomes equal to 0, under this condition quite naturally L bar is equals to V bar, which again says that in the stripping section also the operating line that is going to coincide with the 45 degrees diagonal line. So, therefore, we find that under the total reflux condition, which is the condition where neither a distillate nor a bottom product stream is withdrawn, quite naturally the feed rate to the column is 0 under this condition. Entire liquid from the condenser is refluxed back, entire liquid from the bottom tray it is vaporized, and the entire vapor it is sent back as the vapor reflux. Under this condition, we find that the operating lines they coincide the 45 degrees line as I have mentioned, and in this particular case, therefore, we find that if you draw the stairs, we find that for any particular separation, since the operating lines are furthest from the equilibrium curve. So, therefore, the minimum number of stages are required in order to bring about any particular separation from a known feed composition. And another important thing is that since we are not constructing the Q line, so therefore, quite naturally the minimum number of ideal stages designated as n minimum, that is independent of the feed condition, because we do not need the Q line for this particular construction, right. So, this corresponds to the total reflux condition. The other thing is the minimum reflux. What happens under the minimum reflux? For the minimum reflux condition, we find that quite naturally with the minimum amount of reflux we would like to start. So, naturally under this condition, for any particular feed condition, we will find that the minimum reflux will be achieved when the enrichment section operating line and the Q line, they both of them they intersect at the equilibrium curve. And quite naturally under this condition, if I am drawing the stripping section operating line, and then in that case also we find that all of them they intersect at the equilibrium curve. So, what does this suggest? If you try to make stairs in this particular case, you find that you cannot proceed with this staircase thing, which says that for the minimum reflux condition, quite naturally you would require the infinite number of stages, which I have already discussed, right. So, for this particular condition, if you extend the enrichment section operating line to the y axis, what is the y intercept in this particular case? It is naturally x d by r minimum plus 1. We can write it as r minimum or you can write it as r m. So, therefore, this is the limiting operation. We cannot, in fact, we cannot operate under this condition as well, but we would always like to have a reflux ratio which is less than, rather which is higher than the r minimum, so that the operating line it shifts further away from the equilibrium curve, right. So, therefore, this particular case, the case from where we start from x d x t and the intersection of the q line with the enrichment section operating line that occurs at the equilibrium curve. If we intersect that part, then we find that the intersection occurs at x d by r m plus 1. So, therefore, from this construction we can find out the r minimum. Typically, it lies between 1.1 to 1.5, and we know that this r m it is fixed for a given separation, because for a given separation this x d, x f they are all fixed, the q line is fixed, for that we correspond. Other than this particular construction, we can this geometrical construction, if we can write it down, we can get an analytical expression. Based on this analytical expression also we can find out r minimum. Normally what we do, we first find out r minimum for any particular design, and after we have found out r minimum, then we select some particular r by r minimum, right. So, therefore, r by r minimum it has to be greater than 1. Normally, we prefer it to be between 1, I just had a slip of tongue, I am sorry, r minimum does not lie between this, by mistake I told it, the r by r minimum ratio that typically lies between 1.1 to 1.5, right. So, therefore, we would not like, we would always like to keep it to little higher value, such that r by any particular change in operating condition does not approach r minimum, under which we will get a infeasible operation. So, for design what we do, we first find out the r minimum for the x d, x f and the q point. Once we have found it out, we find out r minimum either by this equation or by this particular construction. Once these are done, then we select a r which is slightly higher than the r minimum, and then we proceed. In one moment we have selected what we do, then we have located the particular operating line, the actual operating line, we have located the stripping section operating line, and after that we start dropping the stairs and we find out the actual number of ideal stages corresponding to the r which is something higher than the r minimum. So, just to summarize, if very quickly if we summarize exactly how we are, means what are the different steps. The first thing is we would draw the equilibrium curve and we would also locate the diagonal line, right. Then on the diagonal line we are going to locate 3 points, mainly x d, x d, x f, x f and x b, x b. After that what we do? We estimate r minimum either from analytical expression that I have shown you or from the y intercept. From anything you can find out the r minimum. Then we select some particular r which lies between 1.1 to 1.5 r minimum. Then corresponding to this particular r, what we do? We find x d by r plus 1, and then from x d by r plus 1 on the y axis and x d x d, we draw the, joining these 2 points, we draw the enrichment section operating line. And after that what we do? We fix the feet condition. So, therefore, we find out, to start with, I have said, to start with q equals to 1, we assume the saturated liquid curve, and then we find out q by q minus 1, and then from this xf we, with the slope of q by q minus 1, we construct the q line, and after that we fix the feet condition and we construct the q line. Once these two lines are drawn, then we construct the stripping section operating line. The basic assumption of McKeep-Tilly method is all these lines, they are straight lines. So, therefore, the stripping section operating line, it starts from the point xb and it intersects, it is drawn till the intersection of q line and the your enrichment section operating line. Once this is done, then we start the staircase construction and we construct the staircase construction for the region, construct staircase, and for the portion before the feet or above the feet, we make the steps between the enrichment section operating line and the equilibrium curve, and beyond the q line we make the steps between the the stripping section operating line and the equilibrium curve. So, this is the way we do, and then we find out the n stripping, we find out the n enrichment, and this gives us the n total number of ideal stages in this particular case. So, just to demonstrate, I have given you a problem, you can try out this problem yourself and you can see that I will just write down the steps are written, following that we can do it. We find that F is equals to 1 kilomole per second, it is orthoxylene which contains 30 mole % toluene. Naturally, toluene is the more volatile component. So, therefore, XF is equals to 0.3. We are operating with a total condenser, and the toluene rich stream means what? It is the distillate. So, the distillate composition is also given in terms of toluene, and we find that the orthoxylene rich stream is what? That orthoxylene rich stream is the bottom product. So, that should contain below 2 mole % toluene. So, therefore, from here we know XB is equals to 0.02. So, therefore, for this particular problem, initially what do? We assume just every time we assume feet is at the bubble point, right. Now, I would demonstrate it, or we would be working this out in this class for R by R minimum equals to 1.2. You can try it for other R's and you can see it. XF, it is written as 0.3. XD I have written down 0.8, XB equals to 0.02, right. The alpha it is given as 2.7. So, therefore, moment the alpha is given, we know y star this is equals to, we had already done it previously, this is equals to alpha minus 1 into x plus 1. So, therefore, corresponding to x equals to 0.1, 0.2 etc., we can generate the corresponding y star values, and I have done it, and this is tabulated in this case. Now, we start with the enrichment section operating line. For the enrichment section operating line, what do? We first we need to find out the R minimum. So, therefore, for finding out the R minimum, just if you can see the entire, this is the operating section line. So, therefore, it starts from XD till this particular point, and then it is extended here. So, this point is the feed point, and so therefore, what is this point? You know the XF point, and so therefore, this point will be corresponding to the YF star XF. You know alpha, you can find out YF star in this particular case, and in this particular case if you do it, you will find that the YF star in this particular case it is equals to 0.536. So, therefore, this particular point it corresponds to 0.536, and sorry, I have written it in a different way, it should be 0.3 and it should be written as xf yf star, which will be 0.3, 0.536. So, this point we know, this point we know, we can extend it. We find when we extend it, here it the intercept is at 0.3653. We know x d equals to 0.85. So, from there we can find out R m. The R m, if you find out, you will find that this corresponds to 1.327. So, we had decided that we will be working with 1.2 R m. So, therefore, we will be working with R of 1.592, right. Now, for this particular case, again we start in the same way. We start with the same distillate composition, and then we extend it to the y intercept of x d by r plus 1, x d equals to 0.85, r is equals to 1.592. So, therefore, you find that the y intercept in this particular case, it corresponds to 0.3653, no sorry, the point it corresponds to 0.25. Just I will be rubbing it off once. Yeah. So, therefore, this particular point, if you observe, you find that this particular point, it is roughly around 0.25. So, therefore, from there we can find out the actual R we have already found out, and more or less this line we have drawn. Then from the feet point, what we do, since we have taken a saturated feet, we draw the vertical line, and after that we know this point corresponds to the 2% toluene there. So, xb is 0.02, 0.02. From here we extend the stripping section operating line. Once we have done this, now we start dropping the number of steps. Please do it yourself. You will find that in this particular process, more or less, we have 3 trays in the rather 3 trays in the enrichment section. In the 4th tray, we find we shift from the enrichment to the stripping section. So, therefore, it means that the feed is introduced in the 4th tray, and the total number of trays are equal to the total number of stages, this is equals to 10. Try it out yourself, and you are going to see that you will be getting this correspond to a reflux ratio of 1.592 for a feed flow rate of this, and the distillate recovery and the bottom composition as specified here. Well, this was the number of ideal stages. Now, if you remember, we had already discussed that in reality the thing that we had assumed that the mass transfer occurs such that the steps they extend from the operating line to the equilibrium curve, that does not happen in practice. In practice, we find that mostly the mass transfer is much less as compared to the mass transfer under this condition. So, therefore, in reality we find that we do not have the mass transfer to that extent, rather we have a little lower mass transfer, right. So, therefore, for each tray if this happens, we find that from yn minus 1, instead of going to yn star which lies on the equilibrium curve, actually the mass transfer happens till yn, and this particular ratio, this divided by this is known as the Murphy tray efficiency. This basically gives us the fractional approach to equilibrium for each particular stage. So, therefore, what we do, if we know the Murphy tray efficiency, then for each and every point, if we know this, then multiplying this with this, we can locate yn corresponding to each particular x, and then through all these points we can draw the actual curve between which and the operating line the mass transfer will take place. and then we would be dropping the stairs not between the equilibrium and the operating line, but between the line that we have drawn and the two operating lines, and from here we find that quite naturally the number of stages, actual stages which are required, which will be much higher as compared to the number of stages that will be required for the ideal stages. Now, this is one approach, or rather one particular definition of the tray, of tray efficiency. There is other way also by which we define the overall tray efficiency, and which defines as the number of ideal trays which are required for any particular separation divided by the actual number of trays which are required in order to bring about this particular separation. Mostly we use this overall efficiency or this overall tray efficiency in finding out the actual number of stages or the actual number of trays. Normally, we find that this overall efficiency, it is a complex function of say the geometry, design of contacting trays, then the flow rates and the flow paths, composition and properties of the vapor liquid streams, etc. And typically from the available industry data, I have noted down a few particular processes and the corresponding eta O or the overall tray efficiencies for the enrichment section and the stripping section. This can be referred to while you would like to find out the actual number of trays. For example, in your particular case, we found that you were operating an orthoxylene column. For the orthoxylene column, the efficiency in the enrichment and the stripping sections can be taken as 80. So, therefore, you have found out the number of trays in the enrichment section, you have found out the number of trays in the stripping section. For each particular case, you are supposed to find the actual number of trays in the enrichment section, which is nothing but the ideal number of stages divided by 0.8. Same thing you are supposed to do for the stripping section. In this case also n ideal divided by 0.8. From adding up these two, you would get the actual number of trays in the total column that you require. Well, so this entire thing I had discussed for one particular reflux ratio. Now, normally what you are supposed to do, normally we would like to go for an optimum design. As I have already discussed that for the optimum design, quite naturally we would be the optimum R optimum, rather we would like to find out the optimized design based on that particular reflux flow rate, which would give us the minimum annualized total cost, as I have told you, right. So, therefore, we select the reflux ratio for the column as the independent parameter in order to minimize the annualized cost. Now, what is this annualized cost? First, let us see what is the total cost. The total cost is equal to the equipment cost, or you can say the capital cost plus the operating cost. What are the things which should be included in the capital cost? Capital cost naturally should include the cost of the column, the cost of the condenser, the cost of the reboiler, right, and also the cost of the pumps. Normally, these costs are much higher. So, therefore, we normally do not include this, and this does not contribute much to the cost. Now, for all these things, there are two things. One is a material cost will be there, the other will be a fabrication cost. Normally, what we do, we can find out the material cost. How you would like to find out the material cost? You know what is the material that you will be using. Maybe for the column, for this particular column, we would go for alloy steel, and then for this particular column, we know that what is going to be the column height. From the column height can be obtained from the column, the number of trays as well as the tray spacing, which I will be discussing shortly after this. So, therefore, once I know the total column height, where I know that the column height is nothing but the number of trays, actual number of trays, into the tray spacing. We would also have to find out the column diameter. Once we have found this out, we can find out the thickness of the shell. The details regarding the thickness of the shell will be discussed in the discussions or when we discuss the pressure vessels. Usually the shell thickness is taken as 5 millimeters, it is not less than 5 millimeters. The thickness is definitely based on the operating pressure. Normally, as I have said, the P operating, this is equals to 1.1 kg per centimeter square, and usually the P design, it is taken as 1.1 times the P operating, which gives this as 1.21 kg per centimeter square. So, from here the shell thickness can be obtained, and so from the shell thickness etc., we can find out the material cost. Usually the fabrication cost and the material cost are taken as equal. So, therefore, for the column, the material cost into 2 gives us the total cost of the column. Same way for the reboiler and the condenser, what are they? They are nothing, they are simply the two heat exchangers. So, therefore, if we can find out the QC, I would put a capital QC, if we can find out QR, the heat loads, then we know that this is equals to U A delta T. In this case also it is the same. So, therefore, if we know the overall heat transfer coefficient, we would be in a position to find out the area. Once we have found out the area, then we can go for the cost data. Now, we are not going into the details of the entire cost. You will not be asked to do detailed calculation, but the concepts etc., which are being discussed will definitely be asked during your assessment questions and during the final exam as well. So, therefore, the condenser and the reboiler costs can also be obtained in this particular way. We know that the QC, this is nothing but equals to the total amount of heat load, which is R plus 1 into D into delta H vaporization corresponding to the distillate condition, and this corresponds to the this delta HV, this is basically H of the vapor D at the dew point minus HL at the bubble point. So, therefore, for the distillate. So, therefore, from there we can find out the latent heat of vaporization, and from here we can find out the Q condenser. Normally, for the Q reboiler, what we do? We know the Q condenser. We know that the total enthalpy which is going out with the distillate. We know the total enthalpy which is going out with the bottoms product, and we know that the total enthalpy which has entered with the feed. So, from these enthalpy calculations we can find out QR. So, therefore, we can find out the total cost which is nothing but equal to the capital cost plus operating cost. Capital cost I have already discussed. Operating cost, among the operating costs, what do you have? You have got the cost of steam as well as the cost of the cooling water. So, therefore, if you know what is the amount of steam or the amount of cooling water that you require, you know the price, and you can assume, say, for a continuous plant, you can assume, say, 8,000 to 8,200 hours per year of operation in 1 year. So, therefore, you can find out the annual operating cost. Now, for the capital cost, you have found out the total capital cost. It comes from the material cost and you can double it by 2, so that you can get the entire total cost, including the material cost, fabrication cost. We do not include the cost of transportation etc. Right. Now, this total cost, from where you get, you either have to take a bank loan, and then in that case, depending upon the loan rate, more or less the loan rate is between 12 to 14%. So, therefore, the annualized capital cost, it is nothing but 0.14 into the capital cost. This is the bank interest rate which you have to pay if you have taken a bank loan, and if you haven't taken a bank loan, you have got the money, you are investing, then in that case the loss of interest that you are incurring because you have not kept in the bank and you are investing here. So, therefore, once you find out the total capital cost, you can find out the annualized capital cost, you can find the annual operating cost based on the total amount of consumption of cooling water as well as your steam. Usually the steam cost is much more as compared to cooling water cost. Once you have found this out, you can find out the annualized total cost by adding the two, and then for each reflux ratio you can generate this. Normally we find that with increase in reflux ratio, as you know, that for very low reflux ratio at Rm, this goes to infinity and then it falls, and it is an asymptotic in this particular way. In order to fix the limits at the two ends, generally we plot n by n plus 1 as a function of r by r plus 1, and the graph can be generated. The problem that I had given you, you can try it out. I had done it just for r equals to 1.2 Rm. You can extend it, you can start from 1.05 Rm to say 1.5 Rm, and for each particular Rm you can generate the n plus n by n plus 1, and you can generate the curve and see for yourself what you are going to get. And after that, if all the details of the cost can be obtained, then definitely I have already discussed that the cost versus reflux ratio, this gives you the capital cost, this gives you the operating cost, from where we can get the total cost, and normally from the total cost we can locate the R optimum value. For this R optimum, it lies between the R minimum and definitely the total reflux is infinity. So, therefore, R optimum is always greater than the R minimum, right. So, therefore, this R optimum, it is located, this is obtained from economics, as I have said, and we find that in practice R actual by R minimum can be less than 1.1, but we rarely adopt that, and mostly we find that this particular flattened portion, it extends for quite some time. So, therefore, we can take up any value of R here and we can operate it. Normally, it is taken, you can assume that R optimum will lie between 1.2 to 1.35 times of R minimum. This value is quite naturally for more difficult separations, and this is for the easier separations, right. Now, once you have calculated the whole thing, after that we have done it for, rather the entire cost has been done based on certain assumptions. What are the assumptions that we had taken? The assumptions one were, we had taken a single pass tray, we did not assume any side draw, and then for finding out the tray spacing, usually to start with we assume that the diameter of the column is greater than 1500 millimeters. And then typically to find out the column height, we know the number of actual stages. We would also like to find out the tray spacing, so that from these we can find out the column height. So, for tray spacing, certain thumb rules are there which will be discussed in greater details when we go for the column internals. For now, it is sufficient for you to remember that usually for diameters greater than 1500 mm, we can assume a tray spacing of 600 mm. Normally, the diameter that you are going to get for your vapor flow rate, for which you are going to opt for a tray tower, will definitely be greater than 1500 mm. So, to start with, you can take up this particular tray spacing, and with this particular tray spacing you can find out the column height. Now, this is the normal tray spacing for different trays. Now, remember one thing, the tray spacing will definitely be different for a feed tray. You need an additional space, as I had said, to allow for vapor disengagement, so that liquid is not entrained. So, normally what we find that for feed trays for circulating reflux streams etc., it is either 1.5 times the regular spacing, which is a minimum of 750 millimeters. Remember one thing, for trays we require manholes through which a personnel can enter and fit the trays, or if any repair or anything is required, the person can enter. So, therefore, whenever manholes are provided, an additional tray space is required. You do not have chimney tray for the moment in your problem, so you need not bother about this. And then after the top tray, the dome which you have, that particular dome, it is usually twice the regular tray spacing. So, for your particular column that you had, in that column we found out that there were 10 trays. Now, remember one thing, out of these 10 trays, one goes to the reboiler, right. So, therefore, actually in the column how many trays you have? You have got 9 trays. Now, among these 9 trays, one was the feed tray. So, above the feed tray you need 750 millimeter spacing. Below the bottom tray you would require, I forgot to mention, below the bottom tray also you would be requiring around 900 millimeters of spacing, right. So, therefore, for the remaining number of trays you can assume 600 millimeters of spacing. For the bottom down comer you can assume 750 millimeters or 900 millimeters. For the feed tray you can assume 750 millimeters. Since there are 10 trays, so therefore, one tray will be provided with a manhole. For that you can assume 1200 millimeters, and then you find out the total column height. It will come to something around, I just check it up, it will be around 8.25 meters. So, from there you can find out the column height. Now, for the cost along with column height, you also require to find out the column diameter. Regarding the column diameter, there are some standard techniques which we are going to discuss in when we are going to discuss the column internals part. So, once you know the column diameter, then you know the column height, then you can find out the column cost, you can find out the reboiler and the condenser cost. From everything you can find out the capital cost, you can also find out the operating cost, total cost. Repeat this particular calculation for different reflux ratios, generate this curve, find out the optimum reflux ratio, and then you can proceed to find out the actual number of stages for an optimized design. So, this completes the discussion on binary distillation columns, for distillation columns distilling binary components. In the next class, we will be discussing the multi-component distillation and how we deal with those particular situations. Thank you very much.